Hi, this is Stan Lyle with MasterMath. During the lesson, you're going to come to some You Try It slides where you're asked to do problems that relate to the lesson. Hit your pause button, try the problem, and then hit the forward key to move on to the answer. I hope you have a really good time today.
Before we start graphing equations, we need to make sure we understand a few concepts. We need to understand what a function is, what domain is, range, what's a continuous function, and what's a discrete function.
Yeah, well, howdy, partners. Here we are out in the range. Yeah, the range, that's the domain of the cowboy and the cow. Maybe a couple of dogs, coyote hidden out there somewhere. And the function of these folks is to roam the range and get those cattle to the market. And wait, my phone's ringing. Hold on a second. Yeah? Yeah. I'm sorry. Okay, we'll get. All right. I'm sorry. It'll never happen again. Hi, hey. That was your mother. She says we're supposed to be doing math, not talking about cowboys. So I guess we'll move on and do some math, and we'll talk about domain, range, and function. Get along, little doggies. Move out of here. We got to do some math, and we're going to start our math by talking about a function. A function is a type of equation, and you've been dealing with equations now for a long time. Y plus 2x equals 6 is an equation, but it's not a function, because a function is a type of equation where we're solving for y. Y equals something. Now we can change this equation to a function real easily. All we have to do is subtract 2x from both sides of the equation, and we'll get y equals 6 minus 2x. And that's a function because we're solving for y. Now a function's kind of like a machine. It's kind of like a meat grinder. This function meat grinder we got here is the y equals 6 minus 2x meat grinder. And this function kind of works like a machine. You put something in at this end, and something else comes out at this end. What do you put in at this end? Well, you put in the x value. You input the x value. And those x values that you input, the whole range of those x values that you input, is called the domain. Now we put that x value, we input it into the machine, and the machine turns it around and converts it to y equals 6 minus 2x, and out the other end we get the output, or the y value. And the whole set of potential y values is called the range. The domain is all the possible input values, all the possible values of x that you could put into the function. And the range is the set of all possible output values. It's the set of all the potential values of y. Well, let's try an example. Let's say we had an equation, x plus 2y equals $8. Well, that's not a function, is it? First thing we need to do is to convert that into a function. And you know enough algebra that you could manipulate that and change it to y equals 4 minus 0.5x. Okay, well now we need some input values. We need some x values. And that's our domain. And we've chosen a series of x values, 0 through 8. And we put those values into the function, and the function spit out our y values. And those are our range. Our domain are the x values that we put into the equation. Our range is the y values that came out of the equation. If we graphed
our x values and our y values, it'd look like this. When x is 0, y equals 4. X is 0, y is 4. When x is 1, y is 3.5. There's 1, there's 3.5. And you can see that our range are the potential y values that come out of the function, and they start down here at 0 and go up to here at 4. And our domain are the x values that we put into the function, and they also start at 0, and they go all the way up to 8.
Now you try this one. Hit the pause button, do the problem, and then hit the forward key to move on to the answer.
All right, we're supposed to determine the domain and the range for the data that's plotted on this coordinate plane. Let's make it a little bit bigger so we can see it better. And I can see that I've got an x value for that point, and it's 1. And I've got an x value for this point, and it's 2. And I've got an x value for this point, and it's 3. And so forth to my last point, and its x value is 9. So my domain, or my x values, are 1, 2, 3, 4, 5, 6, 7, 8, 9. Now for each of those x values, I've got a corresponding y value. That point has an x value of 1 and a y value of 8. And this has a y value of 7.5. And this has a y value of 7. And the last one over here has got a y value of 4. So my range is 4, 4.5, 5, 5.5, 6, 6.5, 7, 7.5, and 8. Here's another equation. 3x plus 2y equals 17. Well, I want to graph this, so I probably need to put it into function form. It'd be a lot easier. I'll just do a little algebraic magic, abracadabra, boof, and I'll determine that y equals minus 1.5x plus 8.5. Well, now I could create a table and I could graph this, but do I really want to look at every x value in the world? I mean, is it really important to me to know what y equals when x equals 1 billion? No, it doesn't. So I'm going to pick some x values that I want to look at, and I'm going to be defining the domain that's important to me, the domain that I'm going to look at. And so this time I'm going to say I'm going to look at a domain of x between minus 1 and 5.5. My domain is x values that are greater than minus 1 but less than 5.5. And you'll frequently see domain defined that way with an inequality signs surrounding an x value. And what that means is that every x value between minus 1 and 5.5 is in consideration. An x value of 1/2 would be in consideration. An x value of 0.2234 would be in consideration. An x value of 5.15 would be in consideration. Any number between minus 1 and 5.5 is a potential x value. Well, let's list a few of them. Minus 1, minus 1/2, 0, 0.5, 1, 1.5, etc., all the way up to 5.5. Now, I could determine, using my function, what my y values were. And those are the y values that would come out of this function. Now, I can determine my range. My smallest y value, which corresponds to my largest x value, is 0.25. My largest y value, which corresponds to my smallest x value, is 10.
So my y values range from 0.25 up to 10. And I could define my range as my range is y's that are greater than 0.25 but less than 10. Now I can graph this. And when I do it, it'd look a lot like that. And you'll see I've graphed this the way I would graph a number line. I've included an open circle at either end of the line, and that's because my line doesn't include that point. It goes up to, but doesn't include that point. My x value is greater than -1. It's greater than -1. It doesn't include -1. It goes up to, but not includes -1. Now, another important thing to notice about this graph is it's a continuous line from this point to this point. And that implies that every point in between those two extremes is included in the graph. And we call that a continuous function, because there's not distinct breaks, but it's a continuous flow of numbers from the smallest to the largest. Every number from the smallest to the largest is included. Well, let's try to make this a little more real, shall we? I mean, I've got an equation here, 3x plus 2y equals 17, and I don't know what it means. I mean, what's 3x mean? And why does 3x plus 2y have to equal 17? Well, let's create a story, and maybe we can make it real. Let's say that x equals the number of cans of tomatoes we can buy, and y equals the number of cans of potatoes we can buy. And the tomatoes are $3 a can, and the potatoes are $2 a can. Well, now this equation starts to make a little bit of sense. We could say that $3 times the number of cans of tomatoes we buy plus $2 times the number of cans of potatoes that we buy has to equal $17. In other words, we've got $17 to spend. We want to buy some cans of tomatoes and some number of cans of potatoes. How many of each can we purchase? This equation would help us figure that out. But now, a couple of things are going to change with our domain and our range. Let's look at that. Our original domain was every number between -1 and 5.5. It was a continuous set of numbers that included every number between -1 and 5.5. But those don't all make sense anymore. For instance, an x value of -1. X is the number of cans of tomatoes that I'm going to purchase at the store. I don't know about your grocery, but my grocery doesn't sell negative cans of tomatoes. So I got to get rid of that -1. My grocery also doesn't sell half cans of tomatoes. So I got to get rid of that -0.5. I also got to get rid of all my half cans in the positive side. And that leaves a domain of 0, 1, 2, 3, 4, and 5. Now let's look at our range. This first value, 10, this first member of my range, results from an x value or a domain value that we had to remove. And if we don't have an input value, we can't have an output value, so I got to get rid of that 10. And a number of the remaining members of my range have fractional values, like 9 1/4. Well, could I buy 9 1/4 diced potato cans or 7 3/4 diced potato cans? No, I can only buy whole diced potato cans. So I got to get rid of all those fractional diced potato cans. And now my domain and my range are different because we're dealing with units that are discrete, that we can't break up into partial or fractional units. So my domain is now 0, 1, 2, 3, 4, and 5. And my range is now 7, 4, and 1. And if I were to graph this, it wouldn't look like this straight continuous line that we've graphed over here, which includes every single point between that extreme and that extreme. No, we've got
only a limited number of members of the domain in the range, and when we plotted them, they'd look like that. I'd only be able to plot 1, 7, 3, 4, and 5, 1. And I wouldn't put a continuous line between these points because that point is not included. That includes a partial can of tomatoes, and I can't sell partial cans of tomatoes. So it's just 3 dots, 3 distinct points. And we call that a discrete function as opposed to a continuous function. Well, I just love these tomato and potato stories. So here's another tomato and potato story that you can try on your own. Hit your pause button, try the problem, and then hit the forward key to move on to my answer. I apologize to all of you who are sick of tomato and potato questions and stories. I personally love them, so we're going to do at least one more today. And in this particular problem, we've got an equation, 4y plus 2x equals $20, that we can use to determine how many cans of tomatoes and how many cans of potatoes we can purchase. 4y plus 2x equals $20. Now, I want to put this in function form, and using a little algebraic magic, I can do that. And I'll find out that y equals $5 minus 0.5x. Now, I could create a graph of that if I had a table of x values and the corresponding y values. So let's create a table. And I need to pick y values to look at. So I'm going to just kind of arbitrarily pick every whole number between 0 and 10 as my x value. In other words, I'm going to consider buying 0 cans of tomatoes, 1 can of tomatoes, and all the way up to 10 cans of tomatoes. And then for each of those x values, I can plug that into the equation and come up with a y value that would correspond to that x value, and that's over here. The x values over here are my domain. These y values over here are my range. Well, now let's think about it. Do all those x values make sense? Well, they do. I could purchase 0 cans of tomatoes. I could purchase 1 can of tomato. I could purchase 10 cans of tomatoes. How about the y values? Do they all make sense? Well, I could purchase 5 cans of potatoes, but could I purchase 4.5 cans of potatoes? No. How about 3.5 cans of tomatoes? Or potatoes? No. So all those half cans of potatoes, all of them are going to have to be eliminated. And that changes my domain to 0, 2, 4, 6, 8, and 10, and changes my range to 5, 4, 3, 2, 1, and 0. Is that a continuous or a discrete function? Well, it's a discrete function because we have discrete units of each of these cans. We can't purchase a half unit. We can't purchase a quarter unit. We can only purchase whole units. So this is a discrete function. You try this one. Hit your pause button, try the problem, and then hit your forward key to move on to my answer. Well, here's a handy-dandy little table and function that would allow us to convert meters to yards. The number of yards equals 1.094 times the number of meters. And the question is this a discrete or a continuous function? Well, to answer that question, you have to ask yourself a question. And that is, am I limited to just whole numbers of meters? Is 1, 2, 3, 4, and 5 the only meter sizes that I could use? How about 1.5? Could I have 1.5 meters? Could I have 2.675 meters? Well, yes, I could. My meters
could run continuously from 1 meter to 5 meters. And the same true of my yards. I can have all kinds of fractional units between the 1.094 yards and the 5.468 yards. So both my meters and my yards are continuous. If I were to graph this, it'd look just like that. I would draw a continuous line between 1 meter and 5 meters, and it would be a continuous function. Well, that's our lesson on domain and range and continuous and discrete functions. I hope you learned a lot. Now it's time to test your skills. Go to www.mastermath.info and try the worksheets and the quizzes that you'll find there. I hope you had a great time. I hope you learned something, and I hope we see you again real soon. Bye-bye.